Okay, wonderful. So welcome back, everyone. We'll continue the discussion on PAC learning today. So we learned about sample complexity for finite H, right? Consistent case. And essentially, we said, the consistent hypothesis is just, when the empirical error of the hypothesis learned from the sample and evaluated on the sample is 0, then it's a consistent hypothesis. And then the consistent case basically says that an algorithm for any target concept C was in capital H and IID sample S, the algorithm will return a consistent hypothesis HS. Okay, so the theory, goes as the finite H consistent case. I would call this a generalization error, right? Because it is basically saying with that very high probability, the true error, which is R of HS, is gonna be upper bounded by 1 over m logarithm of cardinality of H plus logarithm 1 over delta. All right. So this is a generalization error, and the sample complexity basically is here, right? So so the sample complexity is here, which is the equivalent way of saying that generalization error, which is basically saying that with high probability, the generalization error is going to be smaller than epsilon. But now, it's conditioned on the assumption that the number of examples in that hypothesis is greater than equal to 1 over epsilon logarithm of cardinality of H plus logarithm 1 over delta. Okay, so there's two ways of illustrating sample complexity and illustrating generalization error are equivalent. Okay. All right. So some insight about this. First of all, this is a finite H, right? So basically means that you have only a finite number of hypotheses in the hypothesis set. So your consistent algorithm L is a PAC learning algorithm because your M is in the order that is a polynomial function with respect to 1 over epsilon and 1 over delta, right? So remember, recall the PAC learnable definition. That is a very important condition, right? And also, basically, this theorem says that when you have larger M, so your number of examples is larger, you have a smaller generalization gap. And this is essentially, what we've been taught when we're learning machine learning, basic concepts, for example, supervised learning. We've learned about when you have more examples in your sample, which means when your sample is larger, you suffer less from generalization gap, right? So you are, unlikely to overfit, right? So that theorem basically proves why you've learned those concepts when you were first introduced to machine learning, generalization error, or test error and training error, and so on. Right? So the price to pay for producing a consistent algorithm is the use of a larger hypothesis class H that contains target concept C. So I've already talked about this last lecture. Just wanted to quickly remind you, it is more likely that you will get a consistent hypothesis or a consistent algorithm if your hypothesis class H is larger, right? So there is a trade-off. As you can see, if your hypothesis class is larger, you're likely to get a consistent algorithm, but your sample complexity will be larger, right? Because the sample complexity is related to the logarithm of H here. Okay. All right. So logarithm of cardinality of H is the number of bits to represent H. That is, a easy argument. Then often the algorithm can be ERM, so like empirical risk minimization. The reason is that here, if you have a consistent algorithm, basically means that algorithm will get a zero error, right? So your ERM is basically trying to achieve this zero error. That's why algorithm usually is ERM, empirical risk minimization, right? So of course, as you can see, the bound is going to be looser if you have a larger hypothesis class, which is, again, a easy to understand argument. So this is a list of insights I wanted to emphasize. Any questions? Okay, so since we've talked about this generalization error, we've also talked about the sample complexity. Let's use an example to show how we can put these theorem into use in practice, right? So we're going to consider this example, a very, very simple example, conjunctions of Boolean literals, right? So let's say you have 6 Boolean variables, x1 through x6. Of course, you could imagine I could use x1 through xn, right? But let's use x1 through x6 because it's easier, for illustration purpose in this example. So they're Boolean, right? So they can take values true or false, or sometimes, you might want to just say this is there 1 or 0, right? But it's just true and false. So now, consider an algorithm. Again, the PAC learnable, it is, basically is like existence of such an algorithm. So I'm going to provide an algorithm. So the algorithm is so-called learning conjunctions of Boolean literals. So what do I do? So I want to start with everything. So what do I mean by everything? I have Boolean literals from x1 to x6, and we're going to include itself and its negation. Okay, so it's x1 and x1 negation and x2 negation. This is something I initialize. You can think about this as my initialization. Okay, right? Of course, this is going to be wrong, but this is something we started to search for. So this is the initialization. All right, so with this initialization, what we're going to do is we're going to rule out literals that are incompatible with xi, yi. Xi, yi is just the ith example in your training data set. Okay, so let's say you have such a training data set on the right-hand side as I'm showing here. Okay, so what do? You basically, let's say 1, 2, 3, 4, 5, 6. You have 6 such examples. So actually, this might be confusing. So look until the slide. Okay, so you have 6 such examples, so the first example is x1 taking value 0, x1 taking value 1, x3 taking value 1, x4 taking value 0, x5 1, x6 1. And then the result, which basically means is, the result of the literal, right? Conjunctions of these Boolean literals. So it's the expression. So what is the expression? The result of the expression is going to be giving you true. So can you tell me what you can rule out for this example here? Right? So for example, if x1 is within this expression, then it won't be true, right? Because x1 is false. But if you have one false in your expression, that is, if you have one Boolean variable in your expression that is false, then the entire expression won't be true. So you can rule out x1, right? Does that make sense? Okay, so you can rule out x1. So can you rule out x2 negation? Yes. What about x3 negation? Okay, what about x4? You can also rule out x4 and x5 negation and x6 negation, right? So after this example, what can you rule out? You can rule out, let me clear everything. So you're getting x1 negation, right? x2, x3, x4, x5, x6. Okay? Yeah, we're only looking at first row right now. True. Okay, so after that, we're getting this expression. So this is what our algorithm is doing, right? Essentially ruling out literals incompatible with xi, yi. Similarly, you can rule out, now let's see. So for the second example, what can you rule out? Notice that there is only one difference here. Okay, so x4, so here in the first example, we're ruling out x4 because taking 0 would make it true, but now x4 taking 1 also make it true. So now I'm gonna ask, what should we do here for the second example? Yes, you're ruling out x4 again, right? All right, so now one question I wanted to ask is, what is the hypothesis? First of all, you have this hypothesis set. How large is the hypothesis set? Hypothesis class or hypothesis set? Now that we've understand what algorithms do, so how large is the H? What's the cardinality of H? Yeah, I write it here, right? So I write 3 to the power n, which is 3 to the power 6. Why? Because you can choose to, for each literal, you can either choose to include it. So x1, for xi, you can either choose to include it, or you can either choose to include its negation, or you can choose not to include it, right? So you have 3 choices for each of this literal, so that becomes 3 to the power n. Okay, so that's the total number of the total size of the hypothesis. Okay, so is this clear? So this basically reviews what's a hypothesis set, and for a finite hypothesis set, how do you calculate the size? Now, since we've went through the algorithm, I'm going to ask you, is the algorithm consistent? Meaning, after running the algorithm, can I get a 0 error on this training data set? The answer is yes, right? So I can get a 0 error on my training data set, just because my algorithm is doing the correct thing, right? So once I rule out the literal incompatible with xi, yi, I will get a 0 error on this xi, yi. Therefore, if I went through every single example, I will get a 0 error in the end. So it's going to be consistent. So now going back to what you've learned so far, my question would be, the hypothesis class size, the cardinality of H. You also know that your algorithm is consistent. What can you use for understanding the generalization error of your algorithm on this hypothesis set? That's a very good question. So someone asked, do we consider only false positive error? So yeah, so actually here, so what would be an error, right? An error, so an error basically means that if you evaluate, so yeah, anyone wanted to talk about how would you define an error here for an empirical error or for a 0-1 loss? How would you define it? So you have an underlying conjunction of Boolean literals, right? So that is unknown, but from that unknown underlying conjunctions of Boolean literals, you would have a label. So those are your target concept. You would have a ground truth label associated with it, right? So now I'm just saying, after running this algorithm, you're going to learn a hypothesis. So what is the hypothesis you're learning? Maybe we can just go through the entire rows and see what's the hypothesis we're learning, okay? So what is the hypothesis we're learning? So we look at the positive ones, right? So for these positive examples, we know how to rule out things because this is the and. It is not an or, so we know for positive ones, if the final result is positive, all the Boolean literals have to be positive because it's conjunction. So I'm gonna rule out, so it's gonna be x1 negation, x2, x3, x5, x6 for these two examples. What about this one? So this one tells me that, there is a conflict. So x4 should be ruled out, and I indeed ruled out x4. So that's fine. What about this one? So this example, I have a conflicting with x3, so I should rule out x3, right? Do people see what I'm doing? X4 is already ruled out, x5 and x6. I don't know how to rule out them. So from the positive examples, this is what I'm getting. So now let's look at this negative example. So on this negative example, we have 0, 0, 1, 1, 0, 1. It's gonna get false. Is this compatible? So if x1 is 0, x bar is gonna be 1, x2 is gonna be false, right? So this is compatible, right? Agree? Yeah, so what about this one? What about this one? Is this compatible with what we are getting here? X1 is positive, so it's gonna be negative. It's also compatible, right? So this is what we are getting after running the algorithm on these 1, 2, 3, 4, 5, 6, on these 6 examples. Agree? Am I making a mistake here? Oh, did I do? Okay, so now once we've learned this expression, so how would you evaluate the error? You're going to get the so-called y hat from these expression on every xi, right? Do you see what I mean? So you evaluating every xi on this expression you're getting, and you're getting a final result, whether it's false or true. So that's like yi hat. So my question is, what is yi hat the same as yi, the ground truth? Yes, right? So because our algorithm is designed that way, we are trying to rule out any incompatible literals. So our literals should be compatible with every single example. So it is gonna be realizable. Okay? Does this make sense now? All right. So here I'm saying that positive examples imply that the target concept cannot contain the literals x1, x2 bar, x3, x3 bar, x4, x4 bar, x5 bar, and x6 bar, right? You cannot contain these literals. This is because, you know, we are looking at the positive examples. We know that this is conjunction, so you can rule out things. However, as you know, it's easy to understand that negative examples are not as informative, right? Because you don't know which one is making the mistake, so you cannot really rule out things. But it kind of serves you as an information that, okay, there is something wrong in this expression. You need to figure that out, but you don't know which one is wrong. When it's correct, then you know everyone is correct, right? This is just the property of the conjunction. Okay, makes sense? All right. So now, you know, we've already seen, you know, this is a realizable and this is a consistent case. Then I'm going to ask you, is this PAC learnable? Why? Is this PAC learnable? Right? Our theory says yes, because, you know, H is finite and you have a consistent algorithm that exists, right? So it is going to be PAC learnable. And what is the sample complexity? Yes, exactly. M is polynomial epsilon. And what's more interesting is that you even know that what is the sample complexity. Although this might not be a very tight bound, but at least you get a bound, right? So without knowing anything about this algorithm or about this hypothesis class, you can, as long as you know that algorithm is consistent, then you don't need to do any analysis. You can only apply your theory to get this result that M is greater than equal to 1 over epsilon logarithm cardinality of H plus logarithm 1 over delta. So that's why this, you know, a generalization theorem is so powerful. This sample complexity theorem is so powerful. Okay, so you not only know that it's going to be polynomial in terms of 1 over epsilon, 1 over delta, you also know it is going to be polynomial. It is just, you know, proportional to 1 over epsilon and proportional to logarithm 1 over delta in this scenario. Okay. Right. So for instance, if you let your delta to be 0.02, so you want a 98, you know, percent of, you know, confidence that it will, your generalization error calculation is correct, then you set your generalization error precision to be 0.1. So you allow 0.1 error. Then, sorry. Then for a conjunction of Boolean literals for up to 10 variables, so x1 through x10, you only need 148 examples. Okay, so this is so-called the sample complexity. As long as you have more than 148 examples, you won't overfit. Okay. just imagine that if you illustrate all possible outcome of the conjunctions of Boolean literals, it will require 2 to the power of 10 examples. Oh, so this is different from, the hypothesis cardinality, right? Hypothesis cardinality is, you can either put the literal or the negation or not include, but here it is the outcome. So for the outcome, it is only true or false. Okay, so you can see the difference here. Okay, so this is an example. This is like an example to show you how you can use the theory we've learned to understand generalization and to understand overfitting, right? Quantitatively, not qualitatively, okay? And in practice, I think what you can do is you can compute this bound and compare with what you are getting in test time. You can calculate your test accuracy and you can compare with this bound. You can see how good this bound is. Okay? All right, sometimes it won't be very, it won't be very tight. It could be a little bit loose, especially when your H is very large. Okay, any questions? Okay, if not, I'm gonna move on to the inconsistent case, which is the case that we think is more practical, because in practice, it's not necessarily easy to find consistent algorithm. So if your algorithm does make a mistake, can you still come up with a theory that you can use, for example, complexity characterization and for generalization error characterization? So the answer is yes, indeed. So we do have a sample complexity characterization for finite H in the inconsistent case. Okay, so in the inconsistent case, like I said, is more practical and it requires Hopfin's inequality. So here, before we give you the theorem, we have to look at this lemma here. What is this lemma? This lemma is the generalization error of a single hypothesis H. Right? So if you have a single hypothesis H, then for any epsilon greater than 0, so it's a precision of how bad your generalization gap is, right? So you can see this is the generalization gap. This is the empirical error. And this is the true error or the generalization error. So the difference is the gap. So we're bounding the gap between the two. And this is the precision. So the probability that this gap is greater than your precision is upper bounded by 2 multiplied with e to the minus 2m epsilon squared. Okay, so anyone wanting to maybe let me know whether you have some ideas of why I have such a generalization lemma, generalization error of a single hypothesis. Can you think of a explanation for this? What does this remind you? Think about this concentration inequalities we've learned. So I'm trying to show you why we've spent so much time working on these concentration inequalities. And this is one example. If you've been very familiar with it, then you will see. Okay, Vaishnavi, right? So am I pronouncing your name correctly? Yeah, Vaishnavi provided the answer Hopfin inequality. People agree? Exactly, right? Remember what is this hat of RH? Is the empirical error, right? It is the empirical error summing over all these examples, right? And what is this R of H? is the expectation, right? So, each of these random variables would have like an expectation of this random variable. And you're bounding like the summation of random variables and its expectation, right? So this becomes the summation of the random variable, and this becomes the expectation. Does this make sense? So this is indeed the Hoffman inequality, right? So you can see using Hoffman's inequality here, you can get this lemma, generalization error of the single hypothesis H. So now that we have this lemma here, what is the problem? The problem is to get the probability of R of HS minus R hat of HS smaller than equal to epsilon greater than equal to 1 minus delta, right? So then the question is, can we apply Hoffman's inequality to the hypothesis HS returned by learning algorithm when training on sample S? Can we do that? Remember the lemma about it is for a single hypothesis H. So the H is fixed. Okay, so you have a fixed H. However, this H of S is not fixed, right? H of S is not fixed. It is indeed dependent on the sample. So you cannot really apply Hoffman's inequality trivially to it. What you need is a union bound, essentially, okay? Any questions or any confusions here? Okay, so we'll explain this better, I guess, in the next few slides. So the solution is that we will need a bound that holds simultaneous for all hypotheses. Essentially, it's a union convergence bound. So this is the theorem. The theorem is very much related to the theorem in the consistent case. And so this is the most important part, right? So this is the error, the generalization gap is essentially square root of logarithm cardinality H plus logarithm 2 over delta divided by m, 2m, right? So this is the deviation, or this is the generalization gap. And the probability of the generalization gap being smaller than this is very high, essentially 1 minus delta, okay? So equivalently, again, you get the sample complexity, which is 1 over 2 epsilon square logarithm cardinality H logarithm plus logarithm 2 over delta. Okay, so actually the proof is very simple. So I can just very quickly go through things. The proof is that, so you essentially want to characterize the probability that there exists such an H, such that the generalization gap is greater than epsilon. So, right, so that's the event you're trying to say, because essentially you wanted to say that for every H, the generalization gap is smaller than epsilon. So you can, instead of characterizing that, you can characterize the probability of there exists an H that the generalization gap is greater than epsilon, okay? So this probability is gonna be smaller than equal to the summation of the probability of, every one of them being greater than epsilon, right? This is just a very simple argument here. We've seen that a couple of times in the previous lectures, okay? So now, what does this remind you? Yes, exactly, the previous lemma, right? The previous lemma says the probability of this generalization gap for a fixed H greater than epsilon is going to be upper bounded by e to the power minus 2 m epsilon squared, which is the Hoffman's inequality application of that, right? So now, once you have that, what happens is that you want to characterize the probability of this thing smaller than epsilon, right? So the gap smaller than epsilon. Of course, because greater than epsilon is upper bounded by e to the power of 2m. Yeah, so again, like I said, because the probability of there existing such an hypothesis that the generalization gap is greater than epsilon, then of course the opposite of that event or the complementary of that event is gonna be like for every h, the generalization gap is smaller than epsilon. So that's why it is 1 minus this term here. Does this make sense? So this is a very important argument here. Any questions? No? Okay, so yeah, so this is just like, 1 minus of that, because, the summation of these, those two events are complementary, right? Okay, so of course you can set that to be greater than 1 minus delta to get the final sample complexity, right? So for any delta greater than 0, for any hypothesis within your hypothesis set, the generalization error or the generalization gap being smaller than equal to this quantity of square root of logarithm cardinality H. So this is nothing but setting this to be 1 minus delta, and you can solve this equation to get the expression of the error with respect to the delta and cardinality of H, right? So you're just replacing the epsilon here. Does that make sense? So you're just trying to solve this equation so to get the expression for epsilon. Okay, so epsilon is gonna be smaller than equal to this. Okay. All right, so that's it. So you can see the now, because you're familiar with Hopkins and you're familiar with this, complementary event argument, then you can easily prove this inconsistent sample complexity and the generalization gap theory. Okay. So any questions?
I had a quick question. Sorry to go back. On that upper, so the upper bound, the 2 absolute value H, that was from the Hopkins lemma. Where was that from? I can't remember it in my notes. Is that from the previous lemma you just said, or was that from the Hopkins theorem that we showed?
It's lemma here.
Got you. Okay, thank you.
Yeah, no problem. All right, so now let's take a look at, the two scenarios we've learned. We have learned the consistent scenario and the inconsistent scenario. Can we compare them by putting them side to side? So you can see the left-hand side is the consistent case and the right-hand side is the inconsistent case. So let's first compare the generalization gap. So what I'm highlighting here, underlying here is the generalization gap, because the empirical error is just 0, right? So this is the true error, but also the generalization gap. Here, on the right-hand side, what I'm highlighting here is the generalization gap. It is not the true error or the generalization error, because the empirical error is not 0, okay? So that's one thing you wanted to remember. Then second is comparison of these two terms. In the consistent scenario, what is the error? The error is essentially logarithm of cardinality of H over M. So in that order. Whereas in the inconsistent case is the square root of that, the square root of logarithm of H, divided by M. All right. So what does this say? This basically means that for a fixed H, right, for a fixed cardinality of H, to obtain the same guarantee as consistent case, a quadratic larger labeled examples or sample is needed in the inconsistent case, just because your algorithm is not as powerful as the one used in a consistent case. All right. So you can see for both of these two scenarios, consistent, inconsistent, and consistent, you can see a trade-off, right? You can see the trade-off between reducing the empirical error versus controlling the size of the hypothesis, right? If your size of your hypothesis is larger, then you are unlikely to get a low empirical error. You are more likely to get a low empirical error, but your sample complexity will be larger, right? So you can see this subtle trade-off between these two. All right. So any questions here? Now I'm gonna move along. Now we've learned, when H is finite, but in a lot of scenarios, even the axis-aligned rectangles, the first hypothesis class we've learned in class, it is gonna be infinite, right? Because you have infinite many number of axis-aligned rectangles in the plane. So the question would be, is efficient learning from a finite sample possible when the hypothesis set is infinite? Right, so actually with this question, then there are a few ideas. Actually, one idea would be, can we reduce the infinite set to a finite set, right? Or can we use the projection over the finite samples to characterize the complexity of the hypothesis? Or maybe there are useful measures of complexity for infinite hypothesis sets. Right? So these are some kind of motivation about why we need to learn these so-called complexity measures for this infinite hypothesis sets. Right? So I'm gonna actually introduce this infinite hypothesis set H. So you can read the chapter in your textbook, but I'm gonna cover Rademacher complexity, also the growth function and the VC dimension. So I will not cover covering number, for example, but with the understanding of the Rademacher complexity, growth function, the VC dimension, you should be very easily understand the covering number argument. Okay, so the ideas are very similar. Now, so the Rademacher complexity is a very high quality bound. It gives a pretty tight bound, although I cannot guarantee that it's not loose, but it is not as loose as other bounds, right? So it is actually also data dependent. It's the only data dependent bound that we're going to learn in this lecture. Okay, so it is data dependent. So that's nice, but the drawback of the Rademacher complexity is that it's oftentimes very computationally expensive, and sometimes is even impossible to compute even the empirical Rademacher complexity. Okay, we'll see some examples later. So that's why people are thinking about relaxing Rademacher complexity, right? So instead of using this very good bound, can I relax a little bit to make the computation easier? And that's why we come up with this growth function, which is purely combinatorial, and it is actually related, very tightly related to Rademacher complexity. After we introduce the growth function, then it comes to VC dimension. It's again another relaxation from the growth function, but it is much easier for us to handle because growth function can also be very difficult to compute. Okay, so also VC dimension is going to be purely combinatorial. As I said, growth function and VC dimension are all data independent. only the Rademacher complexity is data dependent. And the VC dimension is actually much easier to bound or to estimate. If we do have time today, we will review some of the VC dimension examples. But if not, maybe on Thursday. So it is also worth to note that the VC dimension is an upper bound for this growth function. Okay, so this is a very brief overview of what we're going to cover for the infinite hypothesis set H. Okay, so before we go into the details, I wanted to make sure that we're on the same page. So I wanted to introduce a few notations that we're going to frequently use for the next few lectures. First is the input space. So before we have the X and Y, but now let's just put them together. So put them as a tuple. So it's gonna be Z. Z includes both X and Y. This is your input space, and it includes both the feature space and the label space, or so-called the output space, okay? So you have the small z, which is, one input example, okay? Right, so of course, the sample S is again, m such input examples, z1 to zm, okay? So now you have a loss function. Everyone is familiar with 0-1 loss or hinge loss or, cross-entropy loss. All heard about this in your machine learning courses when you're playing with neural nets and so on. So this loss function basically takes, two y multiply y. So basically means that you take two inputs, both are in the output space, right? Or, the label space, and then it's gonna map that into the real, right? So this is a loss function. I use L to denote the loss function, but I'm gonna also use G. So this is a little bit confusing here. I'm gonna use small g to denote the loss function associated with hypothesis H and L. So I'm gonna denote G of xy as evaluating xy on this hypothesis H using loss function L. Does that make sense? So basically, I'm just writing this L of hxy as G of xy. This is just a change of notation, basically. Okay, so but I'm gonna use that a lot in the next few slides. Okay, so now I have the small g, which is a loss function associated with one hypothesis on this loss function L. But I'm gonna denote the family of the loss function associated with H as the capital G. So it's the collection of all the G's, right, on every H. Does that make sense? So this is just the family of loss function associated with H. So when I say G, it has to be associated with a specific H here. Otherwise, it's not defined. Okay? I know this might be abused notation. Sometimes you wanted to say, a G of H or something, but for simple notation, we're just using G instead of like G sub H or something like that. Okay, so hope this is clear. All right, so far so good. Any confusions about the small g and capital G? Okay, if not, I'm gonna continue. So the Rademacher variable. So you have a Rademacher variable. You can put them as a column vector, sigma. Okay, and the sigma has independent, identical distributed independent coordinates. So each of the sigma I is just, taking values from -1 or 1 with the same probability half. Okay? So coordinates are independent uniform random variable. So far, so good. I don't see any questions, so I assume that we're good. Okay, so with this notation, we're ready to introduce this Rademacher complexity. So what is Rademacher complexity? Because I said that, for finite hypothesis, you know how to capture the complexity of the hypothesis. It's just the cardinality, basically how many hypotheses are there in the hypothesis set or hypothesis class. But for the infinite one, you don't know how to characterize it because it's going to be infinite. So you want to capture the so-called richness of a family of functions by measuring the degree to which a hypothesis set can fit random noise. And this is essentially the idea underlying Rademacher complexity. So some of you might have heard about using neural networks to fit random noise. There was used to be a famous paper maybe in 2017 or 16. There is a famous paper on that. So that's called understanding the capacity of the neural nets, right? And also understanding whether it is likely to overfit. So here, the Rademacher complexity is just the richness of a family of function, right? Or you can also understand it as hypothesis set, richness of hypothesis set. So that it measures the degree to which the hypothesis can fit random noise. Okay, so how do they really do that? Here is, okay, sorry, I meant to show you the box first, then the text below, but let's first focus on the box. So let's first see the definition. What is the empirical Rademacher complexity? So I'm gonna first introduce the empirical Rademacher complexity, then it will be easier to introduce this Rademacher complexity, okay? So what is the empirical Rademacher complexity, ERC? So for sample S, so suppose you have a sample S of m examples, and of course I'm gonna denote them as VI because for simplicity, it is nothing but just Xi, Yi. And you have bounded G. Again, now the G, when I say G, you should think of this loss function family that are associated with the capital H, okay? So let's say you have bounded G, and the G is gonna, map from Z to AB. So the bounded G is bounded between A and B, right? So of course, when I say G, it has to be associated with the hypothesis set, which is H, right? So now you're ready to define the ERC. It is essentially denoted as the hat of R. So it's the caddy R, and it's not the R. So, for notation purposes, please distinguish this with the capital R. The capital R of H is just like the true error, right? The generalization error. Whereas the caddy R is, the Rademacher complexity. With the hat here, I'm just denoting the empirical Rademacher complexity. So also it's very interesting to note that this empirical Rademacher complexity depends on the sample. So that's why you have a subscript S here. It is for a fixed sample, okay? Right, so I'm not averaging over samples. For a sample, I can define the empirical Rademacher complexity. And this is measuring the G rather than H directly. However, if you think about this, as I said here, it captures the richness of a family of functions. So basically, I can either capture, think about G as a function, also H as a function, then I can define Rademacher complexity or empirical Rademacher complexity for both, either for G or for H. But I want to start with G because we know that G is going to be bounded between A, B. Okay, let's start with G. Now, anything unclear before I proceed? Okay, so very importantly, I wanted to emphasize here. So the definition of the R hat SG or Cali R hat SG, so ERC, is gonna be expectation over the sigma. Remember what is sigma? Sigma is the vector of the Rademacher variables, right? Each, with the independent coordinates, each coordinate is just taking with equal probability taking either -1 or +1. Okay, so I'm taking expectation over that random vector, and let's focus on what's taking expectation on. We're taking expectation over this inner product. Why can't I write? Oh, okay. So this inner product, right? This is the column vector. This is just my red marker random variable column vector is one realization of that. Now this is another row vector because I have a transpose here. Oh, actually, sorry, my bad. This is actually, I take it back. Okay, sorry. This is my row vector because I write it this way, right? So I write it as a row, right? So each of the column is just sigma 1, sigma 2, sigma m. Sorry, I made a mistake here. So this is a row vector. Now I take a transpose of the row vector. This becomes the column vector, right? So I'm taking the inner product between a row and a column vector, which essentially, becomes the inner product, right? I'm taking the multiplication of a row vector and a column vector, which becomes the inner product. So it's gonna be giving you a scalar, all right? Does that make sense? So I'll give you a scalar, but notice what is the second column vector? The second column vector is the function g for any g within the G class. So you are evaluating on this specific examples, Z1 to Zm. Notice that the Z1 to Zm are just elements of that sample S. So you're not taking average or anything, or you're not looking at expectation. You're not counting the randomness in your sample. And that's why it's called empirical red marker complexity, okay? However, you need to notice that I am actually calculating the randomness in G. Well, it's not randomness in G, but I'm calculating every G in my capital G, right? Because I have to take the supremum over this inner product. So what does this mean? This basically means that so first of all, let me ask you, so if this inner product is very large, what does this mean? You have two vectors, okay? A and B. If the inner product of two vectors are very large, and you know that the amplitude of these two vectors are fixed, let's say, then what does that mean? Yes, it means the vectors are highly aligned and essentially pointing to the same direction, right? Or very similar direction, right? So basically this means a good fit. So basically what does that mean? That means that your G of Z1 through G of Zm could fit this random noise pretty well, okay? Because you're taking supremum here. So what does this mean essentially? Because you're taking supremum over G, so that means you can find such a hypothesis that can fit random noise very well, right? Because the supremum actually tells you that you wanted to find the one that can best fit the random noise. And now the result is gonna be the complexity, right? So the better you can fit the random noise, the higher your empirical red marker complexity will be. And also it's very important to notice that this is taking expectation over sigma. So it's not like one realization of the sigma. You are, in expectation, you can fit these random noise. Does that make sense? So if you were, so now this is not related to data, right? This is basically related to how much you can fit your random noise, how much your loss function can fit random noise, right? This is somehow characterized as the empirical red marker complexity of G. Notice that this is of G, not H, okay? So if you wanted to characterize the empirical Rademacher complexity of H, then you wanted to replace this G with H, and then you wanted to replace this, G belong to G as G belong to, H belong to H, right? Okay, so is this clear? So let me see, someone's asking, so the expectational sigma means for each random noise vector, we know the inner product of the noise and the most aligned G, then average across all aligned inner products. So you wanted to say average over all random noise. Okay, does that make sense? Because the random noise is very random, right? It's just like with equal probability of taking positive or negative, and each of the coordinates are independent. So it's really like spread, how to say, spread, right? It's very random, basically. So this basically means that whether your G could be capturing all the random noises very well. For example, okay, so I think one example might make things better. So, if you're fixing, so within the bracket here, the square bracket here, you're looking at a fixed sigma 1, sigma m, right? So this is fixed within the bracket. Now for the fixed sigma, you know what's the direction. So it's gonna be this direction, let's say. So this is gonna be your fixed sigma, okay? So on that direction, maybe you are able to find such a G that's aligned, with this direction, okay? But since you're taking expectation over sigma, so your sigmas could be on other directions as well, right? So let's say if your G is not very rich, it can only take this direction. So it might give you a very good, fit for this specific sigma, but the G won't be able to fit these other sigmas, right? So this is another other sigmas, because the sigma could point to many other directions. Does this make sense? So taking expectation over sigma basically means that you were able to do a good fit for a lot of different realizations of this random noise.
So this is, we're varying G, but we're keeping H constant, right?
Say that again.
So when you're taking the supremum, that's we're changing G, but H, the hypothesis we're evaluating this on is a constant hypothesis, right?
It's not a consistent. Remember, so you're finding a G within G, right? So because you've chosen a maybe fixed loss function L, so effectively you're finding H in H.
Right.
Does that make sense? Because
right.
Effectively you are doing that. Although I'm just, since I'm characterizing the complexity of the capital G, so I'm focusing on G here. But essentially the richness is basically captured by the richness of the hypothesis set. Hypothesis, yeah.
Okay, thank you.
No problem.
But the set of hypotheses is fixed.
Can you say that again?
The set of hypotheses, like capital H, is fixed for the family.
Yeah.
Yes.
The set of H is fixed, and the set of G is fixed as well, right? In that scenario, you are fixing the L, the loss function. Either using 0, 1 loss or hinge loss or whatever loss you choose. Yeah, each H is basically a training. So you could say H is actually trained, but it doesn't have to be, right? Do you see what I mean? For example, in axis aligned rectangle example, any axis aligned rectangle is gonna be an H, right? It can make a lot of error on the training example. It doesn't matter. Any axis aligned rectangle is gonna be an H. So this does not necessarily have to be related to your S. Do you see? Yeah, okay, wonderful. So is this clear? So, this expectation is very important to understand. Without this expectation, things will be broken, right? You won't be able to characterize or estimate the richness of a family function by measuring the degree to which a hypothesis set can fit random noise using a specific sample, right? So this is very important, using a specific sample, because I'm fixing the z's here. Okay, that's what we mean by using a specific sample S. All right, so now notice that G and G enumerate all G and G independent of sample or learning algorithm like that. So effectively, this is almost like enumerating all hypotheses within your hypothesis set H. Okay. All right. Of course, G is evaluated on S because this is exactly what you are using in your inner product. G of Z1 and G of Z2, and Z1, Z2 are from the S. Right? Okay, so now let's look at this bullet point. It measures how well G, G is associated with H, right? Correlates with random noise on S. And it's describe the richness of G. If you're describing the richness, also you're kind of describing the richness of H, right? And the richer G can generate more vectors, GS, on the sample S. Right? Like I said, this sigma could have many different directions, right? So if your G is able to generate, let me use a different color, maybe. Yeah, if your G is able to generate more directions, then you will, because you're taking supremum over G for every realization of the sigma, so you should be able to get a larger empirical Rademacher complexity because your G can go to many different directions, right? So richer G can generate more vectors GS on the sample S, and thus better correlate with random noise on average. Okay? All right, so I hope this is clear. All right, so now we've understand the Rademacher, empirical Rademacher complexity. So the Rademacher complexity is actually very simply defined on the empirical Rademacher complexity. So the Rademacher complexity is not dependent for a specific sample. It is taking expectation over the sample. Okay, but it depends on the M. So the sample size. So you are taking average over samples of size M. Okay, so when you're taking average, it has to be sample of size M, not M-1 or M+1. It's M, right? So that's why it's called the Rademacher complexity with the subscript M. Is characterizing the complexity of G with on samples of size M. Does that make sense? So here is an extreme case. Of course, this is not a very good illustration of a Rademacher complexity, only because Rademacher complexity is really defined for infinite hypothesis. But I wanted to use this example to tell you, what really this Rademacher complexity is doing. Okay, so let's say you have this very extreme case that you have M equals to 2. You want to characterize the complexity of a sample of size 2. Okay, and your S. So what this is your training data set. Your S is just your sample. They have only 2 data points, as I said, M equals to 2. So if x1 0 and x2 0. So both examples will give you a 0 label. Okay, so x1 is fixed, x2 is also fixed. Okay, and now you're going to use a 0-1 loss function. So what does this mean? Is just that this is the indicator function. It's gonna be 1 if hx not equal to y, or it's going to be 0 if hx equal to 1. Okay, so it's a 0, 1 loss. Now consider h. Let's say you have an h. Oh, sorry, this should be capital H, my bad. Consider your capital H with only two hypotheses, H1, H2. Like I said, again, this is not a very good example, but because Rademacher complexity is very hard to understand, so I wanted to use this not so suitable example to show you what it really is doing. Okay, so it is a finite hypothesis set, but Rademacher usually characterizes the infinite one. So H is just H1, H2. So this hypothesis only have two hypotheses, H1 and H2. So the H1 and H2 both are deterministic. So it always, no matter what's the input, I'm always gonna output 0 from an H1 and 1 from an H2. Okay, so those are deterministic hypotheses. Now, since G, oh, okay. Is it okay that I finish discussing this slide? It won't take maybe more than 5 minutes, hopefully. Thanks. So since G is just the vector of the L of H x1 y1 up to L of H x and ym, right? Then you have G1 0 0, G2 1 1, right? And the capital G is just the entire set of G1 G2, so it's gonna be that 0 0 and 1 1. Okay. Is the supremum in the definition missing 1 over m? Yes, indeed. Sorry about that. That's a very good point. I forgot to include that. Okay, good point. So indeed, there should be a 1 over m here. I think I'm missing it here as well. Okay, yeah, that's a good point. Thanks. All right. So, but that won't affect the result too much. It is just a scaling factor, okay? So now we have, the capital G, which is G1 and G2, the collection of G1, G2. Therefore, how do you evaluate the empirical Rademacher complexity, right? So as I said, the definition is that. And then, how do you evaluate it? It depends on the joint distribution of the sigma. Right? As I said, the sigma has such a joint distribution on the right-hand side. So if you just calculate this expectation by just enumerating all the possible values that sigmas could take, so it's going to be -1, -1, -1, +1, and so on, right? So the 4 different values, then you will see that all of them is going to be like 0, 0, 0, and 2. Okay, and the nice, very interesting here is that you're multiplying with the probability, but you're also looking at the maximum, the 0 and sigma 1 plus sigma 2 here. Okay, so this is nothing but calculation of this. And then based on that, you are calculating the result and you're getting 1 over 4. So this is gonna be an empirical Rademacher complexity. However, in practice, as you can see, because your G is going to be infinite and your capital H is going to be infinite. So it's very hard for you to calculate the supremum here. Okay. Therefore, it is very difficult to calculate empirical Rademacher complexity. Okay. So now if this is what you consider when H is H1, H2. So it has two hypotheses. But if you consider H equals to H1, so this is a much smaller hypothesis, then the empirical Rademacher complexity is going to be 0. Actually, also if you consider H equals to H2, which is again another hypothesis with one element, both H1 and H2 are deterministic. And again, this will give you a 0 empirical Rademacher complexity. So the insight here is just that, although you might have two here in this capital H, let me use blue ink here. So in this capital H equals to H1, H2 here, although you have two deterministic functions, you can still get a non-zero empirical Rademacher complexity, which is 1 over 4. Whereas if you have only one deterministic function, you will get a 0 Rademacher complexity, empirical Rademacher complexity. So basically this means that when you have a richer family of hypotheses, your random complexity and your empirical random complexity are likely to be higher. Okay. All right. So that's the end of today's lecture. So I wanted to remind everyone that after this we will talk about random complexity. We'll also talk about the loss function. And next lecture, most importantly, we'll talk about the VC dimension, okay, and a few examples on VC dimension. I think VC dimension is going to be very practical for our everyday use in machine learning research. Okay, all right, thanks everyone. That's today's lecture.
Thank you.
Thank you.
Thank you.